So first of all, I would like to thank Gediminas and all his collaborators for this wonderful event. It's my first time in Vilnius, and it's a great pleasure to be here. So let me start with just a brief glance of our recent activities. Just if you would like to discuss some other topics at the break, I would be more than happy to do that. So part of our activity is about the physics of quantum disordered systems, in particular Anderson localization and the interplay of localization with interactions in Boson Fermi systems. Another part of our activity is the physics of low-dimensional systems, in particular one-dimensional ones. Here you have an example of a work that we did about the mode transition in a periodic lattice, which has a particular flavor in one dimension, because the strongly interacting gas is strongly unstable against perturbation with a wavelength of the order of the typical distance between the particles. And it turns out that the mode insulator can be stabilized with an infinitely small periodic potential. So this is what we did here. This is the amplitude of potential. This is the inverse of the interaction strength. And then in Monte Carlo calculations, we found some deviation with respect to standard renormalization group analysis that was confirmed by a wonderful experiment in the group of Giovanni Modugno and Massimo Inguscio. So this is a kind of example. What I will discuss today is quasicrystal, which is somehow in between these two cases, where quasicrystals are kind of intermediate between fully ordered systems and disordered systems. Finally, we also have activities on out-of-equilibrium dynamics of correlated quantum systems, and in particular, we studied the propagation of information. Here you have an example of propagation in a 2D Bose-Bard model, which has a particular flavor again in 2 dimensions, because it is governed by a particular matrix, which is not the Euclidean matrix, but the Manhattan matrix. So this has important implications. Okay, so a part of our motivation is the possibility to quantum simulate solid-state physics with cold atoms. So I probably don't need to argue too much that ultra-cold atoms are a wonderful platform to do that. On top of a control of geometry as well as interactions, an important property of this system is that the periodic potential is imposed by external means. So in particular, the interference of laser beams. And a great asset of it is that essentially these systems are perfect, and they are in particular phonon and impurity free. So this is very important. It's first at the basis of the block theory of bands in solids, but it has also been determinant for the observation of the mode insulator transition in a 3D optical lattice in the group of Emmanuel Bloch quite a long time ago now. Okay, so this is what a standard solid looks like. So this is a periodic arrangement of atoms in real space that you can see here. So there are different arrangements depending on the geometry. But the hallmark of this is found traditionally in Bragg spectroscopy in solid-state physics. So this essentially realizes a Fourier transform of this arrangement that translates in Fourier space. I hope you can see the spots here. As a series of sharp spots that are periodically arranged. Then there are other kinds of solids that were discovered by chance by Bragg spectroscopy that look like this kind of thing. So they look like something that is almost periodic, but with some distortions. The important point is that these distortions are not random. They have themselves long-range coherence, long-range order, and this is shown in particular in these Bragg spectroscopy experiments, where you recover some sharp peaks like that, and these sharp peaks in Fourier space is a signature of a long-range order in real space. Nevertheless, in crystallography, there is a well-known theorem that is called the restriction theorem that tells you that discrete rotations, only a few discrete rotation symmetries are compatible with a periodic order, which are rotation symmetries of order 2, 3, 4, and 6. And essentially, if you find a Bragg spectroscopy, a Bragg image with sharp peaks that do not fulfill this discrete rotation symmetry, then you have a quasicrystal. So this is here an example of a tenfold rotation, a tenfold symmetric potential, and this is an eightfold rotation symmetric quasicrystal. So these kind of quasicrystals have attracted a lot of attention in solid physics since their discoveries by Dan Shechtman. And in particular, they have some very interesting properties on top of topological properties. There are a lot of fractal properties, some special transport properties at the frontier between disordered and ordered systems. And a big question is, what about correlated phases when there's an interplay between interactions and its quasi-periodic order? So here we are interested in what happens. So for sure, in solid-state physics is essentially about fermions, like electrons, but with cold atoms, we can also address bosonic systems that give a new aspect to quasicrystals, so in the bosonics part. So quite a long time ago, 18 years ago now, we made a proposal together with Luis Santos to realize a bosonic quasi-periodic system with a Bose-Einstein condensate. So the idea is very simple. The rotation order is determined by the arrangement of your lasers. So in these examples, we used 5 laser beams that are arranged like this. So this creates this kind of quasi-periodic system, which turns out to have 10-fold rotation symmetry. Now, if you load a Bose-Einstein condensate, an interacting Bose-Einstein condensate in this system, then the Bose gas will acquire the quasi-periodic order. This can be shown or demonstrated in a matter wave experiment, so as realized in a standard time of flight. And what happens is that you see the appearance in this kind of time of flight images that were here calculated in a mean field approximation. You see the appearance of these sharp peaks. So this is a signature again of the long-range order, but the rotation order is tenfold, so incompatible with periodic order. The interesting thing here is that the potential itself contains exactly 11 Fourier components, but nevertheless, the gas, the condensate contains much more peaks here, and this is due to nonlinearity that generates higher order terms in the Fourier transform. So because we are in this conference, I should mention that this work was done while I was a postdoc in the group of Maciek Lewenstein, and I was funded by the Hubble Foundation. Okay. So sometimes when you make a proposal, you have to be a bit patient. And the first experiment was realized only 4 years ago, yes, in the group of Ulrich Schneider, who realized a slightly different configuration, but it's the same idea. So here in his case, he realizes an 8-fold rotation symmetric quasi-periodic potential that you can see here. And he demonstrated the emergence of a quasi-periodic order in a Bose-Einstein condensate. So the interference here is made slightly differently. So they just shown the optical lattice for the quasicrystal for different times. So at 0 time, you just have a peak here, which is a signature of the Bose-Einstein condensate. And then after one scattering time of the atoms by the quasi-periodic potential, then you see the appearance of 8 sharp peaks. And then if you wait longer, so another scattering time, then each of these peaks will develop 8 new spots, and so on and so forth. And with this, you create a kind of fractal structure. Okay, so this work, okay, and I was also happy to learn yesterday that in the group of Christoph Wittenberg, they are also interested in this kind of physics. So we'll see some new results pretty soon, I guess. Okay, so motivated by these experiments, we came back to this problem of Bose gas in a quasi-crystal potential, and in particular in the presence of interactions now in the problem. Let me first turn to 1D systems. So the traditional way to realize a 1D quasicrystal is to realize the Aubry-André model. So the idea is simple. You take a strong lattice that will create a tight binding model, and then you shine a second lattice with an amplitude much smaller and an incommensurate period. So this realizes this famous Aubry-André model, which is the archetype of the quasicrystal of a quasicrystal in 1 dimension. But nevertheless, it's not generic. This is a very special system that has very special localization properties. So here, this is still without interactions. Then there is a critical amplitude of the quasicrystal potential. So beyond twice the tunneling rate, every states are extended, and above this threshold, they are all localized with the same localization length, independent of the energy, which is quite unusual. So this system has been realized again in the group of Massimo Inguscio and Giovanni Modugno, and they observe localization in the expansion of a Bose-Einstein condensate. They also realized the same experiment in the presence of interactions in a Bose gas, and they devised a kind of phase diagram that is represented here as a function of interaction strength and amplitude of the quasi-periodic potential. And then they measured various things. Here, this is a measurement of essentially the correlation, the one-body correlation length that is plotted here. So they find that for low interactions and low quasi-periodic potential, they have something that has a quasi-long-range order, so compatible with a superfluid. If they increase the interaction, they lose coherence. So this is interpreted as the Mott insulator. And for if you increase the amplitude of the quasi-crystal potential, you also lose coherence, but now because of quasi-disorder, and this is a so-called Bose glass. So the Bose glass is the emblematic phase in disordered or quasi-periodic systems, which is a special compressible insulator, while the Mott insulator is a compressible insulator, and the Mott insulator is an incompressible insulator. Okay, so you see that this is a prediction that we made for the transition between the superfluid and the Bose glass. It works quite well. It's much more difficult to see what happens precisely for strong interactions. There is a very good reason for that. It's because in these experiments, although they are working with ultra-cold atoms, the temperature effects are very strong. So this is exemplified here, where this is in black the measurement of the one-body correlation function, and in blue is a DMRG calculation at 0 temperature, and you see the strong difference. For weak interactions, they are able to use a heuristic thermal broadening that reproduces quite well the experiments, but for strong interactions, we still find some deviations. The reason for that is essentially that the temperature is of the order of the tunneling rate. It's a bit smaller, but about this, which means that the thermal fluctuations will essentially kill the coherence very, very fast. So the first work we did on that is to try to overcome this problem. So there are two options. Either you go to the experiment, to the experimentalist, and tell them, okay, so lower your temperature. Usually they will not like that much because evaporative cooling removes a lot of particles. There is another way, is to increase the energy scale in our problem, keeping the same temperature. So the idea is very simple. What we did is study what happens now if your two periodic potential are very small and of the same order of magnitude, but still with an incommensurate period. So in all the remainder of the talk, I will always talk about this kind of shallow quasi-periodic potential. The first question we had is, do particles localize in a shallow quasi-periodic potential? And because we are away from the Aubry-André model, so hopefully the answer is yes. So this is the result of an exact diagonalization for single particles. This is the energy of the particles, the amplitude of the quasi-periodic potential. So blue represents localized states, yellow extended states, and we find a transition between these two systems. So you see here a first difference with the Aubry-André model is that depending on the energy, the states can be localized or extended. Okay, there is another very important feature here is the presence of a critical potential that turns out to be of the order of the recoil energy up to 10%. So this is very good for us because it means that now our energy scale is the recoil energy, which is larger than the temperature in a typical experiment. So it means that we can find localization for rather small amplitude of the quasi-periodic potential. Another interesting feature of this system is the fractality of the spectrum close to critical points. So here this is the energy spectrum, and the idea to find a fractal structure is to, for instance, use a box counting method. So the idea is that you cut your spectrum in different boxes with a given size, and you count how many boxes contain at least one state. So if the spectrum is regular, you expect that the number of boxes is inversely proportional to the size of the box. It turns out that in this system, close to the critical point, the scaling is different. It's not the inverse of the size of the boxes, but the size of the box to the power minus 0.76, which is a signature of a fractality in the spectrum. Okay, so let us turn to interacting systems now. So this is essentially the same problem as before, but we include repulsive interactions between the particles. And we study this problem using quantum Monte Carlo calculations in continuous space. And then we want to identify the three possible phases. To do that, we need two quantities. So the first one is a superfluid fraction, which will tell us whether the gas is superfluid or not. And the second is the compressibility. So if I have compressible gas, then I should have Bose glass, and otherwise it's a Mott insulator. So this is a typical result of a phase diagram that is plotted here at essentially 0 temperature, above the critical value for localization. This is chemical potential, and this is the interaction strength here. So this is strong interactions on the left and weak interaction on the right. What we find here is that we have a complex structure of Mott lobes that appear here that are actually reminiscent of the fractality of the one-body of the single particle spectrum, and we can show that these Mott insulators are also fractal with a given fractal dimension. Then for smaller interactions and large chemical potential, we recover a nice superfluid. And here in between, we see the appearance of a nice and very stable Bose glass in between the Mott lobes. You may note that the Bose glass appears below the single particle mobility edge. There is a very good reason for that, is that when you are in one dimension, infinitely interacting Bose gases behave as single fermions. And then localization should be expected only below the mobility edge, which is represented here, and this is indeed what we find. So these are various results of the same kind for different amplitudes of the quasi-periodic potential. And so again, at essentially 0 temperature. Now the question is what happens at finite temperature, because this was my argument at the beginning. So the problem here is that in this case, we have to identify a new regime, which is the normal fluid. So essentially a normal fluid will be non-superfluid and compressible, which is exactly my definition of the Bose glass. So I have to find another way to distinguish the normal fluid from the Bose glass. In the 1D system, it's really relatively easy. The point is that a quantum phase like a superfluid in one dimension can only exist at 0 temperature. So we can measure a number of quantities as a function of temperature, and as soon as we find a dependence in temperature, then we are no longer in the quantum regime. So this is what we observe here. So this is a measure of the correlation length in the 1D system as a function of temperature here. So for starting from the point in the Bose glass somewhere here, so we see that for a certain up to a certain temperature, the correlation length stays stable, and then at some point starts to lower. And the point is that here the thermal fluctuations will dominate the insulating behavior of the system, while in this part it's dominated by the disorder. So this is how we distinguish the various cases. And then at finite temperature, so the temperature that we used here is a typical temperature that was obtained in the group of Hans-Christoph Nagel in Innsbruck. And then we find that the normal fluid will remove the Bose glass and a part of the Mott insulator for very weak amplitude of the potential, but for a relatively small amplitude, we still find a legitimate Bose glass that in principle can be identified in an experiment. Okay, 5 minutes. Okay, so I will skip this part and turn to the 2D quasicrystal. So here, we repeated the same kind of studies, but in the 2 dimensions. So in this work here, the configuration is that of the group of Ulrich Schneider. And this is the phase diagram that we find for weak interactions in this case. So this plot is realized in the mean field approximation. This is the interaction strength. So now here, this is weak interaction. This is strong interactions. This is the amplitude of the potential. And we find a transition between a Bose glass and a superfluid here. In this case, we have weak interaction, so we do not expect a Mott insulator. The color scaling here is the superfluid fraction, which does a relatively good work. Nevertheless, in order to find the transition, you really need some many-body effects and go to Monte Carlo calculation. So here you have an example of the superfluid fraction as a function of the interaction strength. So this is a slice somewhere here. The red line is the mean field calculation with Gross-Pitevsky equation that shows a relatively smooth behavior. So you don't see any transition here. But if you repeat the calculation with Monte Carlo calculations, these are the blue lines here, and the darker is for the largest system here, it's much sharper. It still looks smooth, but if you turn to a log-log scale, so this is exactly the same data, you see that the superfluid fraction drops at a certain point, while the mean field calculation is still smooth. So this is how we identify the transition that is represented by these plots here. So the experiment was recently done by Ulrich Schneider in this preprint here. So they realized this kind of experiment. So this is scattering length, this is the amplitude of the potential, and they find a transition between a superfluid and a Bose glass here. And the results that are here are compatible with our results. You see here that the error bar is very large. It's not because of our calculation, but just because we plotted the thing as a function of the coupling strength, which has a log dependence in the scattering length. So if you plot it as a function of the scattering length, then you have super huge error bars. Okay, nevertheless, we still have a question about finite temperature. So these are calculations that we did in this new paper, going from weak interactions to strong interactions as a function of temperature. So here we have the chemical potential, the temperature for a certain amplitude of the potential. And then we find all these phases, so superfluid and a Bose glass. So this is the typical regime of interactions in the group of Ulrich here. And we identify a normal fluid. Here there's a subtlety is that we cannot identify the superfluid as in one dimension, because in 2 dimensions, the quantum phases survive at finite temperatures. In particular, you can have superfluidity at finite temperature and a temperature dependence of the superfluid fraction. So we have to use another way. And the point is that we just compare to what happens for the same gas in the absence of a quasi-periodic potential. So if we start from a normal fluid, of course, shining a quasi-periodic potential will not restore superfluidity, whereas if we start from a superfluid, as soon as we get something that is no longer superfluid, then we have a Bose glass that is an insulator that is induced by the quasi-periodic potential. For strong interactions, we find a Mott insulator phase that appears here that is highly non-trivial, actually, because we are in a shallow periodic potential. There's no underlying periodic lattice that would support a standard Mott insulator phase. These are just bare results to show you that there are still open questions about this problem. So these are results, so I'm running a bit short, so I will be short here, about the superfluid Bose glass transition. So what we observe is something that seems compatible with the Berezinski-Kosterlitz-Saules transition. So pretty much as in the absence of the quasi-periodic potential, but there is a strong shift in the chemical potential that remains to be understood. Another question is about the Mott insulator phase, as I said, which is highly non-trivial. So it seems to be to have some relation with a single particle problem, but not exactly. You see that there is a shift in the chemical potential, but nevertheless, the plateau is at the same position. So there is a relation that we are investigating at the moment. Okay, to finish, this is just an acknowledgement to all my collaborators. In particular, in red, you see those who contributed to the work that I presented today. And this is the summary of what I just discussed. Thank you very much.
So thank you very much for keeping on time. So we have some questions and comments.
Do you know what happened? Because this was for the unit filling, all of this, right? The phase diagrams that you have shown.
I don't know what is unit filling in this case because I don't have well-defined sites.
Because of the quasi-periodicity.
Yes, because of the quasi-periodicity, and again, I don't have an underlying lattice, so it depends on how you define it. So what I can tell you anyway is that in the 1D case, where we see the appearance of these Mott insulators, so some of these Mott insulators are at unit filling for one of the lattice or the other one. So in this kind of 2 independent Mott insulators that appear, but we also see some other Mott lobes that come from beating between the 2 quasi-periodic potential. And this beating is induced by the renormalization of the effective potential due to the density of the gas. In 2 dimensions, well, I cannot tell you.
Okay. And I understand that potential realization of extended Bose-Hubbard is not possible in kind of in the regime of quasicrystals, because the spacing is way bigger, right? Due to the
No, in principle you can, but in practice the problem is that the temperature is not negligible at all. And the point is that when you want to see something that is related to disorder, you have to be extremely careful about your correlation length, because it can be, well, it depends both on the disorder and or quasi-disorder and the temperature. And if you want to distinguish the two, you really have to be very careful about that. In particular, as I've briefly shown, in the case of the Aubry-André model, the temperature is a real problem.
Okay. So, sorry, because it's a third question. Any kind of charge density waves and will not be able to be observed then in the quasicrystallic structure, right?
Okay,
because
we have not specifically addressed this problem, so okay, I don't have a definite answer. This is a good point.